In this work, we present a benchmarking of structured policies and policy optimization for real-world dexterous object manipulation. Our work is based on the tri-finger platform that has been introduced by Ludwig et al. And served as the basis to the Real Robot Challenge 2020. The goal of the challenge was to promote state-of-the-art and dexterous manipulation on real hardware by providing participants access to a cluster of 7 real robots. This work is built upon the motivation to thoroughly benchmark and compare our 3 successful submissions to the challenge in order to work out what is effective and what not. For this purpose, we focus on the challenge's second phase, which revolves around manipulating a cube using the platform. The first investigated approach is a reactive Cartesian position control strategy. It is built upon the idea that most tasks in the challenge can be solved using carefully designed position-based motion primitives, and thus propose to use the following control law, using the Jacobian stamped pseudo-inverse. The desired velocity in Cartesian space yields from a PID control law to ensure cube pose control. This approach is combined with the so-called triangular grasp, placing the fingers such that they form an equilateral triangle, ensuring force closure and easy manipulability, as the fingers can apply forces on the cube's center of mass in any direction. A second approach to solve the challenge is based on Cartesian impedance control. Using Cartesian impedance control enables natural adaptivity with the environment by specifying second-order dynamics on the difference between each finger's position and the reference. By perturbing the reference position in the direction of the goal location, this control strategy allows for cube pose control. The control strategy has been proposed together with a heuristic center of 3 grasp strategy that places the fingers in the center of 3 out of the 4 faces perpendicular to the ground plane to ensure that the desired motion can be executed without losing contact. Lastly, we investigate an integrative approach based on grasp and motion planning. When attempting to manipulate an object to reach a desired goal pose, the grasp must be carefully selected such that it can be maintained throughout the whole trajectory. To guarantee this, the approach considers several heuristic and randomly sampled grasp candidates and attempts to plan a path from the initial to the goal pose, using RRT in a simulation environment. Once a grasp has been found for which planning was successful, this approach executes the motion plan by following the pre-computed trajectory using PD control. We now showcase the performance of the 3 approaches. Considering the overall experiments conducted in this work, we find that using motion planning provides the best trade-off between accuracy and reliability. Also, as shown in the videos, the pre-computed trajectory results in more robustness against measurement noise of the vision-based state estimation compared to the 2 reactive approaches. Concerning grasp selection, we find that a triangle grasp yields best performance. Further, in the paper, we show the effectiveness of using Bayesian optimization to optimize the method's hyperparameters and investigate augmenting the structured methods with a learned residual control policy.